Okay, so the number of pre-reports for the last thing was just 4. Okay, if you don't come prepared to the lecture, you will not learn it properly. And the grades on your pre-report basically reflects that. I mean, what I'm expecting of you is you should have read the material at least once, thought over it a bit. I mean, not maybe spend the whole week thinking about them, but you should think about the material a bit so that you will have some questions and so that you should have the questions. So 1 basically means you have done what I expected of you, and 0 means you haven't done what I expected of you. And so 0 basically means you will have trouble following what we will be discussing. 1 doesn't necessarily mean that you will be able to follow everything, but 0 you will just sit in the back and not benefit from the course. Or if you don't do your pre-reports, again, you will not benefit from your hours spent in this classroom. And in fact, I was just talking with one of the graduate students about how you should learn physics. Now, that is one problem that I'm really, let's say, concentrating on. I'm trying to read the literature on that. How do you learn physics? Mainly my motivation is for the first-year students. Now, at least my strategy is, you see, if you consider physics, there are almost endless amounts of results and information, etc. So if you concentrate on them, it's essentially hopeless. I mean, you cannot just remember everything. You can only remember the special subject that things on the special subject that you are specializing. But other material, no way. But if you think about the methods we use, there are just a handful of them. There are not many. In your pre-reports for the last week, some of you were asking, it was claimed that this free energy or the Q potential was a maximum in equilibrium. How do we know that it's a maximum? So that there was such a claim in the book. Well, I avoided that question because I couldn't find a derivation that satisfies me yet. I know more, but how do you answer such a question? Well, the methods you can use is, as I said, limited. What does it mean for a function to be a maximum? Its derivative is 0, that is one thing. What else? At a minimum, the derivative is also 0. The second derivative. What does it mean, the second derivative, by the way? You see, I mean, when I was in first year in calculus courses, okay, they always said that, okay, the first derivative has to be 0, the second derivative has to be less than 0. And I always failed to remember the second condition because it just didn't make any sense. Okay, grammatically it's correct, but it just doesn't make any sense to me. Until at one point I saw the explanation. You see, what is the second derivative? It is the rate of change of the first derivative. You see, in a maximum, the first derivative is you start with a positive value, and after the maximum, you go to a negative value. So the first derivative decreases. So in a maximum, the second derivative has to be 0 because the first derivative has to decrease. After that point, I never forgot that condition. So in a maximum, the first derivative has to be 0. The second derivative has to be less than 0. Why do you think I changed the partial derivative to total derivative? Because things get complicated when you have more than one variables. Okay, so you see, when you have, that is the graph of, let me put some color over there. Okay, so here the first derivative is larger than 0. After the minimum, the first derivative is less than 0, so the first derivative has to be decreasing if you are close, in the region close to a maximum. Similarly, for a minimum, the first derivative is negative first of all, so it should be decreasing. After the minimum, it goes up, so the second derivative has to be positive in a minimum. But if you have functions of more than one variable, you have surfaces. So if you are at a minimum, it should be, you can talk about the derivative in every direction, and the derivative at every direction should be 0, and the second derivative in every direction should be less than, should it be less than 0? Let's say, let's assume you have a function of two variables. If x0, y0 is a maximum. Okay, it's an extremum. So its derivative at x0, y0, both of its derivatives. This should be 0 because any derivative in any direction you can write in terms of these two derivatives. That is why just making sure that these two are 0 is enough. What about the second derivative? You see, you have more than two second derivatives. You have the second derivative with respect to x. You have the second derivative with respect to y. You have the second derivative with respect to x and y, and also in the opposite order. Okay, since it's the minimum, if you are moving in the x direction, well, it's just a function of a single variable in that case. It's just a line, so it should go from the bottom. So the second derivative should be less than 0. You can also move in along the y direction. This should also be less than 0. But this doesn't guarantee that all the second derivatives in whichever direction you want is less than 0. Yes, if you want all the second derivatives, no matter in which direction you are moving, to be 0, you also need to have a condition on this determinant. Yeah. You see, the second derivative is now a 2 by 2 matrix. Now this is y squared. So, in fact, the second derivative forms a 2 by 2 matrix. Well, in fact, how many of you remember your linear algebra courses? You see, what are eigenvalues and eigenvectors? They are just the characteristic directions to a given matrix. So, in fact, if you are sure that along the eigen directions, the second derivative is less than 0 in both of them, then you know that you are done. It's a minimum. So what should be the determinant of this matrix? Less than 0 or larger than 0?
I think there's no condition.
Hmm?
Is there a condition?
You see, you might end up having x and y in such directions that your function decreases, but then it increases in the intermediate directions. There is such a possibility. It can be a saddle point unless you have this condition. And this function should be, you see, if you think in terms of the eigenvalues, what we need to have is, well, this is a 2 by 2 matrix, we have two eigenvalues. In each eigen direction, we have basically these two conditions. So the eigenvalues of this matrix should be less than 0, both of them. But the determinant is the product of two eigenvalues. Well, this should be larger than 0. You see, if you want to make sure that in a 2 by 2 matrix at least, if you want to make sure that the eigenvalues are negative, both of them, then that means their sum is negative. Well, that is the trace. So by imposing these two conditions, You're already making sure that the trace is negative. And their product should be positive. If you have two numbers whose sum is negative and their product is positive, then they both have to be negative. So these are the two conditions you have. So let's see. We always say that the entropy is a maximum in equilibrium. Well, you have to prove that you have various strategies. One of them is that the change in the entropy is larger than 0 in a non-equilibrium process. You can either prove this one. Is this true? In a non-equilibrium process, the entropy increases. Because if in equilibrium it's a maximum, then in a non-equilibrium process, the entropy should increase. Is this true? What's the second law of thermodynamics in terms of the entropy?
In an equilibrium system, is it possible that delta S is not changing for a small time?
Okay, let me put it like this. In a non-equilibrium process, delta S is larger than or equal to 0. Is this correct? No? No. Okay, so probably you're all thinking, if he's asking this question so insistently, then there's a trick there. This is not correct, incomplete at least. You see, this is correct for an isolated system, for an irreversible process in an isolated system. That is an important piece of information. You see, as a function, you don't agree?
Is it correct for an irreversible system which is isolated?
This is correct. Delta S is larger than or equal to 0 if you are considering the entropy of an isolated system. In any process, in an isolated system, delta S either increases or remains the same. The second law of thermodynamics. You're not sure? Not convinced?
Yani eşittir şeyini kaldırmalı mıyız diye şey yaptık. O zaten kaldırmamak bir şey değişti.
You see, I didn't say irreversible process. The equality holds only if the process is reversible, or, I mean, when the system is already in equilibrium, entropy basically doesn't change. Well, of course, to show that delta S is larger than or equal to 0, or for any other potential, delta A is less than or equal to 0 in an irreversible process, you have to go into the details of irreversible processes, which are processes that are not in equilibrium. But in this course, we are concentrating mainly on processes that are in equilibrium. So at least this strategy will not really hold for what we have. I mean, we cannot really study these processes using the things that we have learned in this course. But there is the other possibility. Look at the second derivatives in equilibrium. What we had done, for example, we had studied such a system. We divided our system in two parts and then looked at how does each part exchange energy with the other one. So we were essentially looking for the derivative of the entropy with respect to the energy. Well, it was for one of the parts only, but you see, this was E1. This was equal to 0. That gave us one condition for the entropy of the whole. Told us that del S1 over del E1 for the first system as a function of energy, this should be equal to del S2 over del E2. And we identify this as the temperature. Now, this is a condition only for the extremum, not for the maximum. The condition of maximum basically tells us that look at the second derivative of the entropy as a function of whatever is changing during the process. This should be less than 0. In fact, if you go out, this tells you that CV should be larger than 0. So we know that the specific heat of a material is always larger than 0. And you can just look at the other second derivatives of the entropy. Now, along the similar line, you can actually show that the other free energies, the Gibbs free energy, the Helmholtz free energy, they will be minimum in equilibrium. Not just an extremum, but a minimum. Well, as I said, I haven't just come up with a convincing derivation myself. Also here, keep in mind that we are taking the derivative with respect to energy, keeping the volumes constant. You see, entropy is a maximum under these conditions. In an isolated process, meaning energy is constant, the volume is constant, number of particles is constant. Under those conditions, the entropy is a maximum. So free energy, is it a minimum? Depends on what you are talking about, which system you are talking about. You see, dA is minus S dt minus P dV. If dt is equal to 0, dV is equal to 0, dA is equal to 0. So I would say that if you consider processes at constant temperature and volume, A is a minimum. How do you remember which one is a minimum, which one is a maximum? Well, A is equal to E minus Ts. When S is, well, this is at least how I remember it, this is not a proof. If S is a maximum, I would expect A to be a minimum because of the minus sign over there. But of course, in this process, E can be changing, T can be changing, so it's not so straightforward, but at least it's an easy way to remember which one is a maximum, which one is a minimum. Entropy is always a maximum. The other ones will be minimum because of that minus sign. Anyway, this is the second derivation that I should somehow provide to you. The first one was how do you relate the expression for the probabilities to the entropy. This is the second one. This is my homework, let's say. Anyway, back to your questions. Any questions on the previous chapter?
In the previous chapter, we defined phase transitions as the regions where thermodynamic properties are non-analytic functions of
Mm-hmm.
So this is a microstate definition. Anyway. My question is this: can we define phase or phase transition in the microstate?
Well, you see, the phases, any ideas, any suggestions to him? Okay, what do you think? So the first question is, when we talk about, let's say, something is a liquid, does it make sense that, I don't know, two atoms are in a liquid phase or not? Do you think it makes sense?
Not really.
Well, I wouldn't give it too much meaning to that.
But I mean, if we can somehow define it locally, not with 10 to the 23 atoms, but I don't know, 100 atoms, 100 particles, maybe you can define a phase for this kind of system.
Can you define? Sure. I mean, what do you think? Okay, let me not jump to an answer. 400 atoms, does it make sense? If yes, where do you put the boundary? Let me ask you one more question. Let's remember your mathematical physics course. You see, we are defining some partition functions. Okay, we started with In the canonical ensemble, this is our partition function. But when we are looking in the grand canonical ensemble, which we use to study the phase transitions, we define the partition function e to the power minus beta epsilon minus mu n. Okay, this is how we define the partition function. Well, there we have an exponential function. Is an exponential function an analytical function?
It doesn't have, it has only one singularity, right?
Where?
Infinity.
Well, it just has a single singularity at infinity. And does it have any zeros? You see, eventually we won't be dealing with the partition function itself, but we will take its logarithm, for example. Does it have any zeros? This is not a trick question. The exponential function, does it have any zeros except at infinity? No. It's always it's a non-zero analytical function with the only divergence, the only pole at infinity. Well, if you have if you add two functions that are analytical everywhere and non-zero everywhere, furthermore, I mean, it's positive everywhere, you just add two functions, two such functions. Will they be zero anywhere? No. They will have only divergence at infinity. If you add three of them, still the same. They're all positive. The only pole they have is at infinity. You see, the poles are where your functions are discontinuous also. They are non-analytical at the poles. But then we have a sum of infinitely many functions that are analytical everywhere, and each one has a pole at infinity, and they are never zero. How come we end up having non-analytical behavior? That is for you to keep in mind. Now, if we go back to your question, one of the critical things is the thermodynamic limit. You see, phase transitions are regions where something is discontinuous. Either some physical quantity is discontinuous, or its derivative is discontinuous, or its second derivative is discontinuous, etc. But there is some kind of a discontinuity there. Now, if you want to have such a discontinuous behavior, your system should be in thermodynamic limit. Okay, what kind of an example can I give you? Let's see. Tangent inverse. What are the possible values of tangent inverse?
All real values.
From minus pi. Tangent has all real values. The inverse tangent function, minus pi to pi. Minus pi over 2 to pi over 2. X over epsilon. Or let's say x times n. You see, if you take the limit as n goes to infinity, and let's just multiply it with 2 over pi. Do you recognize this function? Well, why did you say 1? You are probably on the right track. That's why I'm asking, why do you think it's 1?
So the tangent inverse takes an infinite. When the argument is
Infinite.
approaching infinity,
Okay.
we have to be approaching pi over 2
Okay.
as an angle, or minus pi over 2.
Okay. So either pi over 2 or minus pi over 2, depending on the sign of x.
Yeah, sin x.
So this is not necessarily 1.
Yeah.
But you got the idea. You see, this is 1 if x is positive, this is minus 1 if x is negative. So this is actually sine of x, which is a discontinuous function. You see, if you don't take the limit n goes to infinity, this is not a discontinuous function. This is a function that changes very fast. You see, for finite systems, the phases or whatever you use to define the phase might be changing very fast, but it won't be discontinuous. So the definition of the phase will be kind of ambiguous in that case. You see, last week when we were discussing the solids and liquids, we said that solids have discrete symmetries. Liquids and gases have continuous symmetries. So that is what distinguishes the two. But if you have a finite gas, finite solid, it doesn't have discrete symmetries. Liquid doesn't have continuous symmetries. So you cannot even use that. So for 100 particles, well, you might try to define some phase convention, phases for them, but there will be always ambiguities there. Like when we were discussing liquids and gases. I mean, you can convert a liquid to a gas continuously if you like. Unless you have both phases at the same time, it's not so easy to distinguish the liquid and the gas phase, unless you have this phase boundary. Just like that, in the case of the finite system, not continuous systems, well, since the phase changes continuously, there will always be some ambiguous points. But you can do other things, for example. I mean, for example, when you look at finite systems, properties change. How many of you have experienced this? How many of you are driving cars? Okay, you are driving. So these days in the morning the air is very cold. Sometimes what happens is when you let the wipers work, okay, they clean the vapor, but then suddenly everything freezes. Because basically you are creating a two-dimensional system rather than a three-dimensional system. And the freezing point of a two-dimensional system can be different than the freezing point of a three-dimensional system. So that's why when you have a very thin film, it might freeze, whereas lumps will not freeze. Where? Defining the phase for a small system.
Yeah, but can't we define some completely different definition? For example, if it's a solid and a particle has, I don't know, 8 particles near, which don't move over time, so we might call that particle solid.
Well, you see, how do you keep them in that state? You see, for a large object, you can make sure that different atoms will not move. But if you have, I don't know, 100 objects, you see, at least the atoms on the surface, I don't think you will be able to prevent them from moving around. So they will move. If they move, the inertia might start moving. You see, as I said, if you go to certain extreme limits, then you can definitely say that, okay, this is this is a solid because it's at almost zero temperature, and you washed it for a certain amount of time and nothing moved. Fine, and nobody will object to that. Or if you are just trying to create something like a potential well around it by, I don't know, lasers, for example, you just create a potential well over there, so that once you remove the potential well, everything just goes out, everything moves away from each other. In that limit, you can also say, okay, this was a gas. But since there won't be any phase transition between these two extreme limits, let's say, I can create a system in which you will agree that we will all agree that it's a solid. I can change a second system, which is very similar to the first one, very similar. So we will all agree that it's solid. Then I can create a third system, which is almost identical in properties to the second system I created. So we will say that it's solid. So this is what I mean by a continuous transformation. My claim is that I can create many such almost identical copies, not exactly identical, but almost identical copies, such that the first copy, we will all agree that it's a solid. The last copy, we will all agree that it's a liquid. So how do you put the line and say that, okay, before this line, it was a solid, after that line, it's a liquid? Phase transitions appear at that line. If you cannot put that line, there won't be any phase transition. So that was one of the problems with the liquid gas phases. We have the critical point, remember? Above that critical point, there's no phase transition. Then the question of, given a substance, how can we say that it's a liquid or a vapor or a gas? Well, we will all agree that a glass of water, it will be liquid. We will all agree that. But if you go a bit deeper, in the sense that I can make many copies, many almost identical copies of the same glass, and the last copy will still be gas. The last copy will be gas. Well, even in that case, by the way, it was probably a bad example, because if you have a glass of water, on top of that water, there's always some gas, water vapor. So there's this interface between the two, which will allow me to say that, okay, on top there is the vapor, on the bottom there is the gas. No, there is the liquid. Yes, other questions? Okay, you see, the first 3 chapters were kind of technically detailed. Basically, you just learned a couple of techniques to study various systems. The 4th chapter was practically there were no technical details. Basically, because the idea was, if you have learned those techniques, it's the same thing repeated again. Now, any questions on any of the 4 chapters? You see, this chapter that we have, that you had the reading assignment for, the quantum statistics, is basically trying to explain the question. You see, in the previous chapters, we had also tried to study certain quantum mechanical systems. I mean, we did study quantum mechanical systems, like we studied the harmonic oscillator. I mean, you studied the harmonic oscillator using the discrete energy values. You studied, in the examples that is, you studied the rotator, and I don't know, the particle in a box. You had studied those. Those are quantum mechanical systems. But there were some, at least formally, there were some shortcomings in those treatments. Like we had just, in an ad hoc way, added the 1/n factorial. We didn't drive it, we just added it. Why? I mean, how can we prove that it should be there in that form? And there were other issues like in the discussions I think it was in the discussions of the first chapter, when we are doing statistics, what we are assuming is that there is the thermodynamic state of the system, and which is parameterized by just a couple of parameters like the energy, the temperature, the volume, the pressure, etc., but just a handful of parameters. On the other hand, we have the microscopic description of the system to specify the microscopic state. We said that, okay, it should be, we have millions of parameters that we need to specify to describe the system. And then we said that, okay, we don't care about those millions and millions of parameters. What we really care about is how many of them correspond to a given macro state. And in the microcanonical ensemble, at least we said that, okay, each one of these microstates are equally probable, and we derived all the rest of the derivation. So that was the initial assumption. But if you think of quantum mechanics, you see in quantum mechanics you have the concept of the energy eigenstate. You see, classically speaking, we can understand that the particles in this in the air in this classroom, they are always moving around, they are always changing their momentum. There is a continuous change in this system, although the total energy in this classroom is, let's say, assume that we isolate this classroom. Although the energy is fixed, there is a continuous change. And then one of the basic assumptions of classical physics is that if you fix the macro state, the system visits all the microstates consistent with that macro state. That's one of the basic assumptions, so-called the ergodic hypothesis. But then in quantum mechanics, we have the concept of energy eigenstate. If the system has a definite energy, the system does not change. So how can we reconcile these things? How can we do statistics under this assumption? Yeah, that is those are some of the questions that the current chapter addresses. So let me start by asking you questions then. Why do we define a density matrix? Why didn't we stick with describing our system using wave functions?
It does not include the classical probability of mixed particles.
What does it mean? I mean, you see, forget the classical physics. We are claiming that everything on the basis is quantum mechanical. So, I mean, we have to start, we should be able to start from the quantum mechanical description and derive the classical result, not the other way around. But you do have a point, though. Why do we need the density matrix? You see, which problems did you study in quantum physics, quantum mechanics, either undergraduate or graduate? Okay, what's the Steigerle experiment?
From you, some silver
Okay.
atoms or sand
Sent where?
to a non-uniform magnetic field.
Okay, let's say this is your non-uniform magnetic field. How do you create these atoms? You have to create them to send them, right? I mean, create meaning, I mean, not create from zero, but
You have all
okay, you have an oven.
and I don't know the dates.
And okay, you have an oven. Neither do I. With a hole. And you have a collimator. So that you only want to have the ones that go through. A collimator you can just imagine as two plates with holes aligned. So that only the atoms that are moving in a given direction will pass through. So what is the state of the atoms you create?
Many states.
You wait a bit for your friends. What are the states of your atoms? Do you know the states? I mean, you see quantum mechanics quantum mechanics in the form that you have learned. Yeah, have you learned the density matrix in quantum mechanics courses yet? No? Okay. Either no or you forgot. Let's say, okay, I mean, once you have once you know the initial state of a particle, okay, given the potential, given the interactions, etc., in principle you can calculate what the wave function at an arbitrary time is. But how do you create the initial state? How do you know the initial state of a particle? Hmm?
You measure it.
How? You see, once you measure the wave function, you just destroy it.
Yes.
So, I mean, measuring doesn't have any meaning in that case. You see, classically, it would be great that you just measure the position, etc. So you don't change the system. But if you measure the quantum mechanical state, you are changing the state.
You create the initial system.
How?
By measuring it.
Oh, okay.
Your time is after the measurement.
Okay, so you measure it, you measure a given property, then you know the state. Okay, that is one way of measuring. How precise is your measurements, by the way? What do you mean very precise?
For instance,
So
you
you-
can precisely measure the up state, for example, on the z-axis.
Okay, so let's also talk about something else. Precise, accurate. Which one? Do you know the difference between these two? Do you know the difference between these two? How can you make sure that your measurement is accurate?
You know, from theory, you have two different outcomes, and you can very accurately
Well,
determine your.
you see, your theory is based on your measurements. So first you have to make the measurement, some kind of a measurement. Well, you see, most of the time your measurement, you can only be sure that your measurement is precise. You can never know that your measurement will be accurate or not. Okay, let's go back to our initial problem. Let's say your friend is saying that, okay, so in this setup at least, I can make sure that, okay, the atom will pass through this collimator, and once it enters this system, it will either go up and then go down. So it will split into two. So I know that this is in which state? Up. Are you sure? There is some hesitation in your.
I think the magnet, but I don't know which one besides this.
Let's say up or down. This is not the whole state, by the way. This is just one property of my system. Anyway, the idea is this. It's not trivial to create the initial state. And most of the time, you won't be sure about the initial state of your particle. And for example, in this experiment, even in this experiment, what you are actually doing is you have many particles. You are not making a measurement on a single one. You see, here, let's say, okay, you are sure that your particle is, let's say, spin up. If you pick up those particles, they will be definitely spin up. And these will be spin down. But let's say you want to study this problem at this stage. Before making the measurement, you want to predict the outcome of your measurement. How do you describe the particles in that region? Well, you can say that, okay, if you want to use, for example, wave functions, there is a wave function. Is there a wave function whose probability of being spin up in the z direction is 1/2, and the probability of it to be in the minus z direction to be 1/2? Is there a state, such a state? You say up. Of course, this is, let me write it in this way. This is z up, and this one is z down. And let's just, for the sake of argumentation, let's assume that half of the atoms go up, half of them go down. So what would you, if you want to write down a state over here, what would you conclude? what kind of a state would you write? You know the probabilities. Half of the probability is the probability that it's up is 1/2 and the probability that it is down is 1/2. What might be the state? Mixture of both of them. What are the coefficients? You see the probabilities are 1/2, 1/2. So the coefficients? 1 over square root of 2 and 1 over square root of 2. Are there any parameters that we didn't determine yet? Sign we didn't determine. Well, in fact, you can put some phase over here. But you see, if this is the state of my initial particles over here, there will be a direction such that if you measure the spin of this state in that direction, it will be h bar over 2. Which basically means that if you rotate your magnetic field, all of them should be deflected in the same direction. If we were using only states to describe the system, and if n were the actual state of all your particles that you are sending into your apparatus, then there will be one direction. I don't know which one. It will depend on what your phi is. For example, phi can be 0. In that case, it will be the x direction. Or phi can be pi over 2. It will be the y direction. But there will be a direction that if you rotate your magnetic field in that direction, all of them will be deflected in the same direction. But that's not what we see. What we actually see is no matter how you rotate your Stern-Gerlach experiment in this setup, the split is always 1/2, 1/2. So the wave function description is not suitable here. So basically what we have here is, okay, you can actually choose any basis that you like. What we know is that the probability of having n is equal to 1/2, whatever n is. This is 1/2, or let me put plus. And the probability of n being minus is 1/2. In any direction. Now, how do we describe this system?
There are many particles.
Yes.
They probably have different directions when they exit the element.
Each one will be in a different state. Some of them will be in the state Psi1. Some of them will be in the state Psi2. Some of them will be in the state Psi3. Not a quantum mechanical superposition of them, but with certain probabilities there will be in one state or the other one. Well, this is also sometimes said they are in a non-coherent superposition. If there is a superposition, then that is a coherent superposition. But then if we want to measure any quantity, well, fine. If it's in the state Psi1, the average of that quantity will be this one. If it's in the state Psi2, then for those particles the average will be this, etc. But then in this combination, we are sending many particles, many atoms. Well, a fraction of them are in the Psi1 state. Well, that fraction is just called the probability of that state, plus P2, plus etc. So the average of any quantity is actually Pi, Psi I, O, Psi2. You see, when I was saying Psi1, Psi2, Psi3, they don't even need to be orthogonal to each other. They're just any state that if I pick up one particle, It can be in either one or the other state. They don't have to be orthogonal to each other. Now here you see, there's an average over here. This is an expectation value. But that's a quantum mechanical expectation value. Quantum mechanical average. But there's another average. That is the statistical average. Statistical because there are many states that my particle can be in. And I'm just averaging over all those single states. You see, in general, this is not equal to you cannot even find a state whose average will give this number in general. Now this is called a pure state, meaning that there's a single state that I can use to describe my particle. This is a mixed state. Essentially, there is not a single state that I can use to describe the properties of my system. It's just a mixture of different states. Then, of course, this O I can write as pi psi I O psi I. Again, some technical computation. Let's say O and I can use some identity. We say identity is just a sum over the eigenvalues of any operator that you like. Just pick up an Hermitian operator. The eigenvalues of that Hermitian operator will give me a complete set, meaning that I can write the identity matrix in terms of those eigenvectors. It doesn't have to be energy eigenvectors. Just pick any Hermitian operator. Then I can just insert two identities. Now, the idea over here was, you say, this is a property of what you are measuring. But here, this is a property of the system. If you know that those quantities, those properties of the system, you know everything about the system. So you can predict the outcome of any measurement. That is what we call the density matrix. This is the O and M. This is rho M N. And rho is usually defined as the operator O. So in this sense, the density matrix is more general than just using the wave functions. And anything you can do with the wave function, you can also do with the density matrix. Just pick up one of the pi's to be 1, all the other pi's 0, so you get a pure state.
Can you think all the atoms in the whole as a pure state which has some probabilities like this? Because you can quantum mechanically make an outer product of every particle in the universe, I think.
Mm-hmm.
You can reduce the universe into a single wave function, get all individual particles outer product. Can you without using this some density thing, can you represent them as a single pure state?
Let's see. Let's try to follow your reasoning. What you are, if I'm not wrong, what you are asking is, okay, I have my system, and then I have the rest of the system, rest of the universe. Well, for everything, I should be able to write down a wave function. And so can't I do it only for my given system? Is that the question? Okay, let's simplify it. Yeah, that's what we do in physics most of the time, right? We just try to simplify the problem. Let me just consider this state. I have my system and the rest of the universe. Let's just say that those are just two spins. Spin up, spin down, plus spin down, spin up. Okay, this is my the wave function of the universe. Now, using this wave function of the universe, can I write down a wave function? Let's say the first one is for A, the second one is for B. I know the wave function of the universe in this simple example. Can you write down the wave function for the system A? So just like in your claim, you are saying that my atoms are entangled with the rest of the universe. Here, my system is entangled with the rest of the system. What is the wave function of the spin A? Can you write down a wave function? Oh, sorry, this is a square root of 2.
You can have some probabilities, but
I can only have probabilities. If I'm looking at my system A only, this can be with half a probability, it will be spin up. And with half a probability, it will be spin down. This is the density matrix for my system A. I cannot talk about the wave function of my system A. But I can talk about the density matrix for my system A. If you make any measurement for your system A, that measurement can be described by this density matrix. You see, if you are making any measurement on the system A in your system, well, just like using the wave function, I can use the density matrix for the combined system. I can write it in this form. Just multiply the density matrix with whatever you are measuring, the matrix corresponding to whatever you are measuring, and take the trace. Now you see here, what I wrote was rho mn o n m, but this is nothing but summing over all n m, but this is just matrix multiplication. When I sum over n, it's just the mm element of the product, but mm element is the diagonal element, and I'm summing all of them. So this is the definition of trace. Well, that's what I used over here. Now, when I'm taking the trace, I have to take over the trace over the degrees of freedom of A and the degrees of freedom B. Degrees of freedom meaning quantum numbers that belong to A only and the quantum numbers that belong to B only. Well, this I can separate. Just take a trace over the quantum numbers B only and then A. But this is since the operator A, the operator O, is an operator that acts only on the A system, not the B system, I can take it out of the trace over the B degrees of freedom. So this is what we call the rho of A. And in the simple example, this will be what you get. So for this simple system, we have seen that you cannot talk about the wave function of your system, even though you can talk about the wave function of the larger system. And still the question of whether we have a wave function of the universe is, well, do we or don't we? We don't know.
But it's still an option, right?
For this system, you see, in this system, there is no option of using the wave function.
You don't need to know the wave function of single. In the ensemble, is there a point that we need to know the single wave functions of each atom sample?
They don't even need to have each single one. Well, we don't need to know the wave function. And we cannot even know them. Well, you claim that we can measure them. What once we measure them, we are modifying them. Even if you say that, well, you can precisely measure them, well, there will still be certain uncertainties.
But I mean, we can kill the classical probability and make it inside the quantum one.
Well, you see,
Is that an option? Is that a correct option?
well, whatever you talk classically, it should be derivable from quantum mechanics. Depending on how you create your system, you might be able to just make sure that Pi is 1 only for one state and 0 for the rest. But in most cases, it won't be easy. And you don't even need to, for most, at least in statistics. Well, you see, when we are creating this one, building this, we weren't so careful about specifying its properties. We are not. So we need something that we can use instead of the wave functions themselves to study such systems. Okay, let's give a break here, and then we will continue.